Okay, so we are nearly done this unit. So let me do a quick recap of what we've done in this large functions unit. I would say there's three main things that you normally have to be able to do. First thing you need to be able to do is look at an equation and tell me some properties of a graph, which is pretty common. Like most of the first questions on the test or on an assignment are, here's an equation, graph the thing. Right? Like that's the first main thing. The second thing you need to be able to do is to be able to solve an equation. Sometimes that's in your graphing calculator where you find where two graphs intersect each other. Sometimes we can do that algebraically, and I've been encouraging you to not just do the graphing calculator method because there's a good chance that on the diploma and even on my test that I'm going to give you a question where it's like find their mistake in somebody else's work. You guys know the question I'm talking about there? There's also, sometimes you have to be able to solve a word problem, and that may even involve having to do the whole L1, L2 exponential regression, like plot points on your graph kind of thing. So this is actually the second slide on your notes here. This is a list of all of the outcomes that I'm supposed to teach you. I just thought I'd point out the things that I'm supposed to teach you, and this is one of the things I find frustrating. It's fairly generic. Well, like here's the outcome. I need you to know how to represent data using polynomial functions. Well, you could represent that in an equation, a table of values, a graph. Does that make sense? So long story short, you have to know how polynomial functions work. You have to know how exponent and logarithmic functions look. And then today we're going to start building our way into doing sinusoidal functions. But like they pretty much all say the exact same thing, don't they? Where it's like basically, do you know how these functions work? Graphs, equations, tables of values, that sort of stuff. Two of these things you have to be able to solve. So you have to be able to solve anything involving a rational equation. You guys remember what rationals are? Yeah, this is actually the unit, the very, very first unit, doing fractions. So I won't assess you on this right now, obviously, but you have to be able to solve rationals, and you have to be able to solve exponentials. Okay. And then lastly, you need to be able to do logarithms. And notice how those log laws work. For example, if I gave you log 6 plus log 2, you would tell me that that's the same thing as log 12. Because 6 times 2 gives 12. That makes sense. So today, essentially, we're going to start working on this last one here then. What do sine graphs look like? What does it look like when I talk about a, quote, sinusoidal function? And so here's just our quick recap of what we've covered. Rationals are fractions. Okay, these ones we do not graph. No graphs on this one. This one's algebra only. And so that was our first unit. Polynomials, exponential, and logarithmic are what we worked on for the last little while. And you have to be able to graph and solve all of these guys right here. The last function we're going to do today is sinusoidal. And sinusoidal is graph only, no solving. So you don't have to worry about trying to solve this for x. You just have to be able to graph them. Okay. So, I mean, with the characteristics we've done before, you still got to know domain, range, intercepts, asymptotes, etc. There's actually 3 new properties I'm going to show you today. The properties are known as the period, the amplitude, and the midline. And these are properties that only apply to sinusoidal functions. So that's kind of where we're going to end today's lesson, though, talking about some new properties of this graph. Does that make sense then what the expectation of like this unit has to involve? Essentially, you need to be able to graph a whole bunch of things. Some of them you have to be able to solve, and you should be able to like do word problems as well. Okay, so I want to start today then just with some review. Today's topic is just reviewing angles. And the reason why we need to review angles is that sinusoidal functions are based off of sine, cosine, and tan. Now, in grade 11, you guys should have done a little bit of work with trigonometry. I don't want to rehash all of it because not all of it's relevant. But I would like for you guys to be fluent in knowing how to graph cosine and sine. Those are the 2 things I want us to be able to do. You may know how to do tan because you've heard of tan before as well, like part of the SOHCAHTOA issue. But we're only going to do those 2 in dash 2. Dash 1 does the tan ones as well. So these things, though, they involve this symbol right here. Do you guys know that little, yeah, like, Do you know what the Greek word for it is? You guys ever heard of theta before?
Yeah.
It's not really relevant, but in case you've never seen this before, this little like circle with a line through it is theta, and it basically means how many degrees there is. So what we're going to be working with now is a function that involves things typically that go around in circles. And so we need to measure angles. So that's today's lesson is let's review some angles before we get too deep into these functions. So here's my first slide. This actually comes directly out of my 20-1 and 2 notes. So some of you guys may have even seen these slides before. Whenever we want to talk about an angle, we sometimes put it on a grid, like an XY coordinate plane. And so we always put one side of the triangle along the x-axis, and then the other arm of the triangle can kind of go just wherever it wants. We call that a terminal arm. Do you guys recall this from last year a little bit? Okay. This is known as being in standard position. If I were to ask you to guess at how much degrees there is right there, could you take a stab at it? Estimate how many degrees there is there?
45.
Yeah, maybe 45, 50 degrees, give or take. Does that make sense? Okay, so this would be known as what's called standard position, where the vertex, which is this little corner right here, this is a vertex, it lies right in the center of the grid. Okay. Let me show you a graph that's not in standard position. This right here might also be 45 degrees, but it's not in standard position because one of the sides has to be directly along the axis. Does that make sense? Here's also one that's not in standard position. If I were to give you a graph that looks like this, sure, I put this side along the axis, and that side right there, and that's 45 degrees. You see the problem is the vertex isn't right through like the center of the grid. You guys seen that before? Okay. Okay, you can have positive and negative angles. So here's an example of a positive angle. This is more than 180 degrees. You can go all the way around the circle to here, and that would be like, say, 225 degrees. But you could go backwards around the circle and call it a negative 135 degrees. Both of those are kind of valid ways of representing angles. Okay. Long story short is that if you go counterclockwise around the circle, if you go quadrant 1, then 2, then 3, then 4, that's known as being like a positive. If you go quadrant 4, then 3, then 2, then 1, if you go backwards, then it's a negative angle. That's all. Maybe you've heard the phrase coterminal angles before. Basically, coterminal angles refer to angles that are like in the same location, but they got there through different methods. I like to visually demonstrate this. See how I put it. Okay, I am facing that way, okay? I'm going to do a jump like this. How far did I jump? Yeah, I'd say that was 90 degrees. Does that make sense? How far did I jump?
Over 360.
360 plus 90 more. Now, I'm facing the same direction, though. Does that make sense what I'm saying here? Right, like, for anyone who's a snowboarder, or a skier, who, like, they have to do, like, flips and twists. Any of you guys do snowboarding or skiing? Like, you know what a 1080 is?
Oh, I know.
Okay, like, what's a 1080? Does that mean anything? What was that?
An axle.
Okay.
360 degrees.
Okay, like 360 is going around a circle once. 720 is going around a circle twice. A 1080 means that you go around in a circle, like, say, 3 full rotations. Does that make sense? Coterminal refers to the fact that, like, what I just did there is I could just turn 90 degrees, and I'm facing that way, right? Or what I could do is a full circle and still be facing that way. And since I'm still going the same direction either way, those are considered coterminal to each other. So if you look at my picture up on the board here, here's an angle that's 130. If I was like a snowboarder or a skier and I did like a full rotation and then did 130 more, these two angles are considered to be coterminal to each other because they both have like the same angle in between, just one of them went around the circle once more. That's all. Does that make sense? Long story short is that coterminal angles, you just always have to add 360 to it. So if I asked you what the next one of these things would be, just add another 360 to it. So that would be 850. 850 would be go around the circle twice and then go an extra 130 more, right? Just like how I tried to do a turn and a quarter. It's actually pretty good, eh? I almost stuck it. All right. Okay, here's where people usually get a little bit lost. Stop me when I lose you. I'm probably going to lose you. Most people are fairly good at working in degrees. Degrees are fairly intuitive for little kids to work with. Like, for example, when I asked you guys to try to figure out how many degrees there were right here, you guys are able to figure out that it was 45 degrees just because, I don't know, you're familiar with that. If I were to ask you how many degrees this happens to be right here, you might say, I don't know, 10 degrees. If I asked you how many degrees this angle is right here, you might say just over 90 degrees. You know what I mean? Like, you guys are pretty good at estimating degrees. Here's the problem. Degrees are actually not the only way of measuring angles. There's another way of measuring an angle called a radian. And I need to help you learn how a radian works for this course. Which sucks, because for so many years of your life, and for probably the rest of your life, all you're ever going to care about is degrees. But basically, for a month and a half, you need to know what a radian is. Fair enough? So let me kind of walk you through a little bit of history. Degrees, I think, are very nice to teach little kids on how to measure angles because, I mean, you guys know, how far is it all the way around a circle? 360, right? One of the reasons why that works really nicely is that if you want to divide it into quarters, each one is 90. You know, those are kind of like nice round kind of numbers. I think one of the reasons why 360 was picked as like how many degrees is in a circle is because it's close to how many days are in a year. There's 365 days in a year, and the Earth goes around the sun, right, in 365 days, which is pretty close to 360. So we kind of make a circle be 360. But other than that, degrees are actually very arbitrary. Like, why 360? Why is a circle not 100 degrees? Why is it not 7,092 degrees? That makes sense what I'm suggesting here. Degrees are actually very, very arbitrary. The other reason I've heard as to why degrees work really well is because so many numbers are divisors of 360. 360 can be divided by 1, obviously, but it can divide by 2, 3, 4, 5, 6. It doesn't divide by 7, but it does divide by 8, 9, 10. It doesn't divide by 11, but it does divide by 12, 15, 18, and 20. So like 360 degrees works really well because so many things divide by it. But other than that, 360 is pretty much completely like just pull a number out of your butt kind of concept, right? Like we'll just go with this as being what a circle is. Does that make sense? Truthfully, as far as I've learned in doing some research here, radians are actually probably the original method of measuring angles. And they're a lot more scientific, but they're a lot harder to estimate. If you want to try to estimate something in radians, most people are not very good at that because it's not nice round numbers like 90 degrees, 30 degrees, that's 360 degrees. Usually it's some sort of really bad version of a decimal number. And so long and short of what I'm trying to say here is that degrees are nice. Like they're nice round numbers, but they ultimately are arbitrary. And there's not really any rhyme or reason as to why we picked 360 for degrees. Like, not a really good reason, at least. Okay? Radians are actually probably more accurate and more precise to work with. But the downside is it's more challenging, so they suck. Okay? So let me try to explain to you now what a radian is. Thousands of years ago, when someone was trying to measure an angle, I don't even know who, they came up with a conclusion that they were going to measure this length right here, this length right here, and they put an angle in between those two sides. And they figure that if the arc length around the edge of the circle that you'd make by kind of making a circle right here, if all of these measurements right here were the same, then that is known as a radian. Let me try to do an example here. Let's say that I made this side right here be 2 centimeters, and I made this side right here be 2 centimeters. Then it means that the edge of like the piece of pie should also be 2 centimeters. And that means that this angle in the corner right here is now defined as 1 radian. As opposed to being like, say, 72 degrees. So, almost, yeah. It's not perfectly a triangle because of the fact that it's like rounded around the corner, but that kind of makes sense, right? As to that's the definition of like one angle. We call it a radian nowadays. Okay. I've got a picture here somewhere. No, I don't. Okay, maybe, can you guys find this picture here? This one's probably the best one. Here's a picture of how this would look on a circle. If whatever this length right here is matches whatever this length right here is, and also matches the edge around the end here, it actually has been determined that you can fit just over 6 of these inside a circle. I like to call it with my Dash 1 class, this is like the perfect piece of pizza. Like, it's not too big, you're not being a pig and having like a massive, you know, like you're cutting off like a third of the pie to eat, right? But it's not like that little thin one that you get where you're kind of getting gypped. Like, this is a nice, reasonable size slice. Does that make sense? Basically, it's been discovered that you can fit about 6 of them in there. You can fit 1, 2, 3, 4, 5, 6. And then they did the math and they figured out that you can actually fit 0.28 of a radian in that last little bit. Like, so someone's getting the short end of the stick piece of pie. So there's about 6.28 radians. And that's how many would be the same as a circle, which would be 360 degrees. Well, you can already see why we would not work with radians. Because 360 degrees, nice round number. I can teach that to a kid in grade 1. And they'll be able to figure out angles. You know what I mean? Like, my daughter is 3. She's turning 4 soon. I bet you she can figure out angles in the next year or 2 of her life. You know what I mean? Especially if they're nice round numbers. But if I told you that a whole circle was 6.28, boy, that's a big can of worms. First, they have to know how to read decimal places. They have to know like hundredths and tenths. And like, that's challenging. But there's actually a really good reason as to why it's 6.28. And I want to show you that, but I think I need to go back a slide. Yeah, it's on this one right here. So if you guys can find this slide here. Here's the reason why. Do you guys know the formula for circumference of a circle? It's listed right here. It's 2 times pi times the radius. You guys seen that formula before? The circumference is equal to 2 pi r. Well, if the arc length is supposed to equal the radius, it means that whatever this length right here is supposed to equal that length right here. What ends up happening is you would then have to divide by the radius because the arc equals the radius. Since the arc length equals radius, you end up doing a math where you divide by the radius. And so it means that the angle you get is equal to 2 pi. That's what a full circle happens to be. Well, what's pi?
3.14.
Yeah. So if you take 2 and you times it by 3.14, 6.28. And that explains why you can fit 6.28 perfect slices of pizza inside a circle. But again, hopefully you can get what I'm saying here. That's not easy stuff to just do on a daily basis, right? If I were to ask you how many degrees that door is swung open right there, I would say the door looks like it's swung open about 90 degrees. But if I asked you how many radians it's swung open, I would say, okay, well, first I got to measure 1 perfect slice of pizza. It's more than that. Is it 2 perfect slices of pizza? No, it's less than that. So I'd say like 1.3 radians. Does that make sense? Like, it's a lot harder to estimate things in terms of perfect slices of pizza. Let's just do an example of that. So I'll put this guy right here, and I'll put this guy right here. Estimate how many degrees that is. I think it's got to be more than half of the 90, right? So 50 or 60 maybe? Would it be cool if I said like, say, 60 degrees, give or take? How many radians would that be?
No clue.
Well, I mean, if I kind of estimate it, does it not look like the edge of that slice of pizza there?
It's like 1.
Yeah, basically 1 radian. I'd say that one's not bad to work with, right? But let's say that I asked you to try to figure out an angle that goes down here. So we're talking all the way around to there. Well, if I asked you to estimate degrees, hopefully you do something like this. You'd say, well, that's about 180. Anybody know what the bottom line pointing downward is? 270, yeah. So I might look at this and guess 250. And you're probably in the ballpark, right? Now the question is, well, how many perfect slices of pizza can you fit into that? Well, I'd go, well, you probably fit like 1 around to there, and then another 1 around to there, and another 1 around to there, and another 1 to there. Maybe you'd have 4 radians, give or take. But would you agree that like that's a lot harder to estimate?
Yeah.
Right? So you can see like this is why radians is not useful anywhere, other than the fact that I have to teach you it for your diploma. So Learn it for the next month and a half, and then honestly you can forget it. And then one day you can impress your friends at parties and tell them how angles actually are supposed to work. No, it's not an impressive party trick.
You can tell them that math is like pi. And then they'd be interested.
Okay, so let's do our first task here. I need you to be able to convert between radians and degrees and know how that works. Okay. So here's the formula you need to write down somewhere. How many degrees are in a circle?
360.
How many radians are in a circle?
57.
Nope. It's about 57 degrees in one radian. So how many radians are in a full circle though? It was 6.28, which is known as 2 pi. So what you can do is you can say there's this like correlation here where 360 degrees is equal to 2 pi's worth of radians.
So would you do pi?
Let me show you how I'll do this in a second here. I'm a big fan of teaching kids to do this using unit conversions. So I'm going to times by a fraction. And if you've been in one of my chemistry classes or physics classes for a little while before, this is what I teach them as well. I'm going to put a number on the bottom that has a degrees symbol so that this degree symbol and that degree symbol can cancel. And I'm going to put RAD, radians, on the top because then this degrees will cancel that degrees and you're left with radians. How many radians are there? Well, there are 2 pi worth of radians for every 360 degrees. So what you have to do in your calculator is take 30 degrees times by 2 pi and divide by 360. And I'll grab a calculator here to show you how that would look then. So take 30 degrees times by 2 times pi, which is 6.28, divide by 360. You get about 0.52, which I think kind of makes sense in a way, right? Because I had it on a slide back here. Sorry that I'm jumping around so much. I am jumping a lot. 1 radian is about 57 degrees. So if you were only doing about 30 degrees would be, you know, like roughly half of that. Then you'd have about half of that perfect slice of pie. So that's about right. So do the same thing here. How do you convert 120 degrees? Well, you times by 2 pi, that's how many radians there are, in 360 degrees. See how your degree symbols cancel? What do you get?
2.01.
No, let's call it 2.19 radians. Okay, I should point something out. I'm going to write the word RAD afterwards to indicate that it's in radians. Sometimes it's implied that if there is not a degree symbol, then it is in radians. It seems so silly. But if you see a degree symbol, then it means it's in degrees. And if you have an angle measurement that does not have a degree symbol, then it implies that it's in radians instead. So often we don't actually write RAD afterwards, but I'm okay if you do, because it takes a little while to kind of train your brain to be able to work with this. Okay, anybody tried the last one as well?
2.7 rounded to meters.
Sure. So 2.7 perfect slices of pie in 153 degrees. Does that work? Cool. That one's the easier one of the two. The other one will actually work. The only downside is that you need to be very comfortable with using brackets properly. Because here what we have to do is we have to convert out of radians and into degrees. You see how none of these things here actually have a unit next to them? If they don't have a unit, it implies they're in radians. So I'm just going to write it next to it here. That's how many radians there are, which means I want to put radians now on the bottom of my fraction and put a degree symbol on the top so that I can cancel radians and end up with degrees. Well, what numbers go here? There are 360 degrees in 2 pi radians. Don't go too fast on this, though. I want to point out a common mistake.
I made a mistake.
Yeah.
5.27 times by 360 divided by 2
Well, you need to put a bracket
pi.
on.
Did anybody do that?
Yep,
Yeah.
Oh, no, actually, I did not get that. It's 2 times.
I got that.
Yeah, okay, so if you did what I just typed in here, that's about 3,000 degrees. And I think I'm pretty comfortable in saying that 5 pieces of pie is not 3,000 degrees, because 3,000 degrees means I went around the circle like 7, 8 times, right? So the mistake is this. You got to do 5.27 times by 360 divided by bracket 2 pi. Your calculator is very literal. It thinks that you want to divide by 2, but then times the top by pi. So you got to put both of these in a bracket. And then it gives you, like, say, 302 degrees. Good. Did that make sense, everybody? Okay, this is less likely on the -2 diploma, but I still want to show you anyways, because like I say, I want to cover my bases in case. It's possible they might give you a radians number that has pi as part of the number. Let me show you how this might look then. If I give you 5 pi over 6, you're still going to times by 360 degrees and divide by 2 pi. But here's a nifty trick though. You see how there's a pi on the top of the fraction right here and on the bottom of the fraction right there? They cancel. So you actually don't have to type pi into your calculator at all.
So, but it would change the answer.
No, so long as you do brackets properly. So I might say let's do 5 times 360 on the top and divide by 6 times 2 on the bottom. I got 150. So I doubt they're actually going to give you something with pi as part of the fraction. They might though. They might. I can't guarantee that. So it's actually not that hard. You just do like say 3 pi over 8 times by 360 divided by 2 pi. Cancel out pi and do bracket 3 times 360 divided by bracket 8 times 2. Make sense so far? Okay. I need for you guys to be comfortable working with both radians and degrees when we graph this thing. So now I want to transition to a little bit of, let's start looking at what these graphs look like. Okay. So what I want to remind you of here is that sine and cosine are the two that we're going to work with today. They are operations. In the same way that you can add, subtract, multiply, divide, last week I would have taught you about the logarithm operation. A log is just something that you put in front of a number that changes the value. Kind of like a square root, kind of like a squared. Well, sine and cosine do the exact same thing. So now we want to talk about how to sine a number, just like you can square or divide a number. So, quick reminder in case you don't know this sort of stuff already. You guys have heard of SOHCAHTOA before? All right, here's just a quick picture to remind you of how that works. What sine actually is doing is it's finding you a ratio of how far the opposite and hypotenuse are compared to each other, or the adjacent and hypotenuse, or the opposite and adjacent. That's where that whole SOHCAHTOA business came from. I'm not too focused on that. We don't really work with the geometry. Like everyone in Math-1 or -2 last year should have done at least some amount of trigonometry. We don't do like SOHCAHTOA stuff, but I just want to point out there's like it still uses the same terminology of sine and cosine. So, okay. Let's try finding some of these values then. If I ask you to find the sine of 30 degrees, well, then just grab your calculator. And the first thing I want to point out, though, is you have to make sure that your calculator is going to calculate a degrees value. Have you guys been shown before where to find the difference between degrees and radians? No, it's under, here's the second button. Next to it's the button called mode. Press mode. And then the second one down is a toggle between radians and degrees. For the last while in your life, you've probably always been told to put it into degrees. Now that you have a bit of an idea as to what a radian actually means, we can toggle back and forth. But for right now, though, can we stick with degrees just to start with?
That's the thing that always used to mess me up when it was on radians.
Right, because it gives you every single answer is wrong. Right, because 1 radian is actually 57 degrees. Like here, let me show you one here. If I do the sine of 57, it gives you this value here. And then if I go to mode and switch it over to radians and do the sine of 57, then it's something completely different, right? But since 57 is about 1 radian, if I do the sine of 1 radian instead, then these two numbers here are actually about the same as each other. So you have to be pretty comfortable in terms of like toggling back and forth between degrees and radians, because you're probably going to be assessed on either, maybe even like both at the same time. So let's try it here. Let's find the sine of 30. All this is an operation to a number. It's finding you the relationship between the opposite and the hypotenuse. and so this one's 0.5. Let me just talk about how that works, just in case it matters here. If you were to put an angle in standard position, you know how sine is opposite over hypotenuse? This right here is your opposite. This right here is your hypotenuse. It means that your opposite is half as big as your hypotenuse. That's what that value is finding for you here. If this is 30 degrees, your opposite is half as big as your hypotenuse. Let's try another one. Cosine of 62. Well, I mean, it's easy to type in, right? It's 0.469, give or take. Here's what that means. Do you guys remember how cosine works? Remember the SOHCAHTOA thing? Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. If I were to draw you an angle right here about 62 degrees, it means that your adjacent is about 0.469 as big as your hypotenuse. Which I think that's about right. You know what I mean? Like if this adjacent right here, if it was, I mean, it's just under half. Does that make sense? The hypotenuse is always the longest side. You guys have heard that before? The hypotenuse is always the longest side of a triangle. Yeah. So basically what you're doing is you're figuring out how your adjacent compares to the hypotenuse. Now we can still do that with like a large number, like 1830.
This one's confused.
Okay, well let me start first by figuring out what 1830 really is. 1830 means if I subtract 360 and keep subtracting 360, and I'll just do it again, and I'll do it again, means that it's
equal 30.
30 degrees. But this is like, you know how I tried to do a full loop around the circle here? It looks like this is actually going around the circle like 5 times and then going 30 degrees. But all that means is that when you draw your 30 degrees right here, it means that you go around the circle 1, 2, 3, 4, 5, and then you go 30 degrees more. So it's actually the exact same angle as the top one. So when you calculate the sine of 1830, it's literally in the exact same spot as the sine of 30 degrees. So it's 0.5. Because when you finish that, your opposite is half as big as your hypotenuse. You can even do this with negative numbers. You can cosine, for example, a negative 0.80. So what I need for you guys to be able to know is, oh, hang on, not 0.80, cosine negative 80. What I just need for you guys to know is that when you type in a sine and cosine button, what it's really doing is telling you what fraction, what percentage of the side of the triangle is it compared to the hypotenuse of the triangle. Let me draw one here. Negative 80 degrees would be like about that. Makes sense? That's about 80 degrees in there. It's not quite 90 because 90 would be like a full square, so that's 80 degrees. Here's the hypotenuse. Here's the adjacent. Hopefully you guys would agree that the adjacent is very small compared to the hypotenuse. How small is it? 0.173 compared to the hypotenuse. That makes sense? So, cosine and sine are just operations on numbers. Okay. I think I'm going to skip most of this slide here. The only difference between this slide here is that when you type this in your calculator, you cannot type in sine of 8.2. Well, you do type that in, but you have to go to mode and change it back to radians. Why do I know I have to change it to radians?
Because of the decimal.
Not because of the decimal. There's no degrees sign, okay? If there is no degrees sign, then it implies that it's radians. It won't actually type in the letters RAD for radians, but it implies that it's in radians. So then you actually get 0.94. If you do the exact same work in degrees, like kind of Shodi, I think you were saying earlier here, it's not 0.14, because that's the kind of mistake that like you might have made in the past, where like you're in the wrong measurement. Is that good so far? So you guys can type in the other ones if you really want to. Okay, so now what I want to do is for the last little task here, I want to start figuring out what these graphs look like. Because that's ultimately the outcome I have to teach you. I have to teach you how sinusoidal functions, how they look as a graph. So we're going to try to graph the sine of x. So I need you guys to go to y equals clear out all the crap that's left over from whenever you worked there before, and type in sine x and then close the bracket. Don't press graph just yet. We have to talk about a few things here. Well, you pressed graph already, apparently. Okay. Well, why don't I just press graph on mine, and we'll see whether mine looks like what Tate's looks like.
Yeah, that's what mine looks like.
So far, it looks like there's just a little bit right there and a little bit right there.
That's not what you got.
Okay, now I'm going to make one subtle change, though. I am currently working in degrees. If I change over to radians, one subtle change, I haven't changed the graph. Now look at the graph.
Oh, OMG. Why? Why like that?
Sinusoidal graphs are waves. They go up and down, just like a surf wave, I guess.
Heartbeat.
Sure, heartbeat monitors actually work similar to this sort of concept, where it's got like an up and down pattern to it. Okay. Now I want to talk about why there's a difference between the two of those. How many degrees are there in a circle? 360. When I was on degrees, a whole circle takes 360 degrees, but my window looks like it's only going to 10. So there's a bit of a problem here. A circle takes 360 degrees. My window size was set for 10 of those degrees. That's why I was not seeing much of a graph. That makes sense? But right now, we're set to radians. How many radians are there in a circle? 6.28 or 2 pi. I want to just go to our window size right here, and I want to make a subtle change. Can we make our negative number go, like, say, to 0 and make x min 0? And then I want to make my x max be 2 pi. Literally type it in as 2 second pi. Like, actually type that in with a pi. If I press enter, by the way, it'll change it to 6.28 for me. Now take a look at the graph I just made. See how it goes up, down, and back up again? That is basically 360 degrees. You know how when you draw a circle, you draw the top half of the circle, and then you draw the bottom half of the circle? Well, that's what's happened right here. Here is like the top half of your circle. And I know it's kind of screwy, but like this is kind of like the bottom half of your circle. Does that make sense? If I were to change my window and make it like, say, 4 pi, how many of these up and down things would you expect if I made it 4 pi? Well, a circle happens every 2 pi. So if I now make it to go to 4 pi, I should see it go up, down, back, up, down, back. See how there's 2 of these things in here where it goes up and down, back again, and then it repeats itself, up and down, back again. Does that make sense? That's how a sine graph works. It basically does this up and down repeating pattern. If I were to change this, though, and make it go mode degrees, now if I look at my graph, I hardly see anything. Because it's not in degrees. I mean, now it's in degrees, but how long does it take for a circle to go up and down? Well, it takes 360, right? Currently, my window is set to go to 12 degrees. Well, how much is that graph going to move in 12 degrees? Not very much at all, right? But if I make my x max now to go to 360, now watch. Now it'll go up and back down again like it's supposed to. So the first thing I need for you guys to be able to figure out is how to make your window sizes reconcile. If you're working in degrees, you have to go up to at least 360. Sometimes you have to double that and go to, like, say, 720, 1080. Does that make sense? But if you're working in radians, you don't want to go to 360. Watch what happens if I change this guy right now to radians. This is kind of cool. Now it kind of looks like a heartbeat monitor. So shift your thing back to radians, but still have your window size go to 360. What's really happened here is you've made your window so stretched out that this graph that goes up, down, up, down, up, down, up, down, it's doing that so many times because you know how a circle in radians, there's about 6 of them? Well, now if you go to 360, this thing's going to go up and down 100 plus times because you're not going to 6.28, you're going to 360. So you have to be able to figure out how to make your calculator reconcile to what you're looking for. So here's the suggestions I'm going to give. If you're working in degrees, well, let's start with radians because I'm on radians. If you're working in radians, try to set your window size from 0 to 2 pi. Here's the other thing, though. You don't need your Ymin and Ymax to go so big. I usually go from -2 to +2. That's usually where I start with. Now you can change that if you like, but it gives a nice graph that looks like this, where it goes up and down and back up again. It has that kind of wavy pattern to it. Does that make sense? However, if you're working in, which one are we in right now? We're in radians, right? If you want to flip it over to degrees, and you just press graph, it's not going to work so great. So then the advice I'd give you is in your window, don't go to 2 pi, go to 360. Because there's 360 degrees in a circle. And now you can see the graph kind of do its up and down sort of pattern. So my last goal today now that we're kind of exploring these graphs a little bit, is to talk about some of the characteristics. So I think, how many slides do I have left? 1, 2, 3? Okay. So let's talk about these characteristics of sine, cosine, and then we'll call her quits here. What's the domain of this graph? Anyone want to take a stab at that? Yeah, because the graph goes from negative to positive, like it goes in all directions, it is element of the reals. And I should point something out. When it comes to figuring out which quadrant it goes from into, really it goes from like as far, okay, let me show you this. If I made it go from -360 to 360, the graph will start over here and it'll just keep doing this up and down pattern forever in the negatives and forever in the positives. So you really can't tell me which quadrant it starts or ends in because it goes up and down forever. So you know how I asked you to do like from quadrant 3 to quadrant 1? We can't do that on this sort of graph. Because this graph will just repeat. No, there's no end behavior. Does that make sense? Like it's always going to go up and down and up and down, right? The range, however, is very different. Do I have graph way, way, way down here? And I'd say no. Do I have graph way up top up here? I'd say no. What's the biggest number this graph seems to get to? Anyone want to take a guess as to how high that peak is? You can see this little notch line next to it. It's 1, because 2 is the top notch line. So it gets as high as 1 and as low as -1. So what this means is that your range is between -1 and 1. And I usually suggest that you read it like this. 1 is the lowest number. -1 is the lowest number. Y is the biggest number. And Y is kind of in between them. That's typically the way that we're going to write the range of this thing. It's a very unique range. Unlike just saying that Y is just greater than or just less than, it's in the middle of two numbers. Visually, can you guys see where the y-intercept looks like it's going through? Yeah, it actually goes through 0. And there should always be a y-intercept. However, there's a problem with the x-intercepts. There are a lot of them. In fact, there is an infinite number of x-intercepts. Because the more the graph goes, the more intercepts there's going to be, because it's always going to cross up and down. And so with my Dash 1 kids, I teach them something called a general solution. For you guys, I just need you to get the concept that like there are so many x-intercepts that we're just going to calculate just the first couple of them. So like what you could do is what we've always done before. Second, calculate the 0. And we'll just calculate at least the first one, maybe the one after that. Oh, shoot. No, it's still working. Okay, so it looks like it's at 180 degrees. I'm in degrees still, by the way. I don't know if someone else is in radians. But it looks like one of my x-intercepts is at 180 and 0.
I got -180
Okay, -180 would also work.
and then 0.
0 and 0 is another one. But it looks like there's another one that's showing up right about there too, right? So I just want to find that one as well. Second, calculate your 0. So what I've done on tests before is I might ask you to calculate the first x-intercept after the y-axis, something like that. I got one at 360 if anyone was able to find that one. Okay. The point I'd like to make here, though, is that the x-intercepts, etc., you're never going to be able to calculate all of them. Does that make sense? Because there's going to be another one after that, and another one after that. So usually I'll just ask you to calculate some of them. Okay. So here's a question then. Are there any other important characteristics?
Yeah.
Yeah, so those are the three. Can I leave those ones? No, you know what? Let's do this here. There are three other ones we need to talk about then. Okay. They're known as midline, amplitude, and period. Okay. Why don't I define them for you on this last slide first? You might even intuitively know what these mean. The midline of a graph is if you were to take a line and put it right dead center through the middle of the graph, where would that be? And hopefully you'd agree that, wouldn't that be this x-axis right here? Isn't that like right dead center through the middle of the graph? Well, we usually write that as an equation. I would say that the equation then is where y equals 0. Where y equals 0 is right dead center through the middle of this graph. Now you might think, well, isn't it always going to be that? Tomorrow I'm going to show you some other examples. Like if I, for example, added a 2 to the end of the graph, can you see how the graph right now is it's up a little bit higher? Does that make sense? So it is actually possible to have the middle of the graph be like way up here. If you can envision it, this graph is probably going up top like that.
So it's the middle of the drum.
Yeah, does that make sense? Like, here, let me change my window. Let's make this go up as high as 4. Tomorrow when we focus on these graphs some more, where would the middle of this graph be? And hopefully you'd agree that it's going to be right about there. That would be where y equals 2. If I were to put, like, say, y equals 2 in a different shade right here, you see how I can put a line, like, right dead through the middle of it? That's a midline. Make sense? So write it as an equation as, like, y equals something, and it's the equation that goes, like, right to the middle of it. So far, so good? Okay. Amplitude basically is about how tall the graph is. How tall is a graph? If you're a surfer, the taller the wave, the better the surfing you might have. Does that make sense? Now, you might have like little beady waves. Well, I can make this graph have taller waves, and I'll show you again more about that tomorrow. But if I were to throw, say, like the number 5 in front here, I'm just going to change my window a bit. Do you see how the graph now has taller, more exaggerated waves to it? That changes the amplitude. And so amplitude is defined as, like, once you find that midline, amplitude is how tall or how shallow is that wave happen to be. Does that make sense? The last little bit is period. And period is sometimes also known by the term frequency. Now, they do mean different things, especially in the physics realm. But basically, period refers to how often do these waves come around. And maybe the best way of diagramming that would be to show you a couple of examples. Here is one graph. And here is a second graph. Which one has more frequent waves? Number 2, right? Does that make sense? What we would say then is that the second one has a shorter period. The period between them is short. From, say, here to here, that might be, say, 7. Well, from here to here is only 3. So this one right here has a shorter period. Period meaning, like, how far is it between occurrences? Does that make sense? That works? Okay. So let's go back and just talk about the other characteristics here then. Let me go back to my regular old sine graph. So sine x. Yeah, the length of time that it takes for this thing to repeat itself, right? I mean, I don't know. Period has other connotations too, right? I mean, how long does it take for a cycle to repeat itself? So let's start with the midline on this graph here. I think I already told you that one, right? Where does the midline of this graph go through? Right at 0, I think, right? So that's y equals 0. The amplitude. The amplitude is how high does this graph get? Anyone want to take a stab at that? How high did this graph get up to? 1, yeah. So the amplitude is 1. It got as high as 1 and as low as -1. Now, we don't figure out how far it is from the highest crest to the lowest valley. We find where it is from the middle line to the top. Maybe the best example I can give of this is, anyone ever gone to like a wave pool? You know, like a big Calgary wave pool kind of thing? If the water was flat, this is where it would be. Okay, to figure out the amplitude, compare it to where flat water would be, and then figure out how high the wave happens to be. Now it's going to go up and above. Like here's where the normal water line is, right? The waves will go above where they should be, but they'll also go below where they should be. Now we don't calculate this as your amplitude. You calculate from flat water to how high it happens to be. That's your amplitude. So this guy's amplitude is 1. The last one is the period. How long does it take for the cycle to repeat itself? Anyone have an idea on this one? Go ahead, give it a try.
It'd be the distance between the two intersections.
Yeah, what we could do is we could find like this part right here and this part right here and find the distance between them. How would you find those points right there? They're maximums, yeah. So can you guys on this half of the room, can you find the really far back maximum? And you guys over here, can you guys find like the one that's just on the right side? I'll do one of them here. Okay, I calculated this maximum here to be at 90.
Are you guys in radians?
I'm in degrees right now. What are you in? Okay, did anybody find this one way back here? So I have this one as 90. Anyone find what that one is?
What's your radian?
Mine's really screwed up. Mine's way back here at -2 to +8 and -360 to 360.
Oh. Okay. That's why it looks different. So mine doesn't look like that.
Okay, well, why don't we all go on the same window size? Let me go from -360 to 360, and I'll go from -2 to +2, like I kind of suggested before. So you kind of have this graph like this. Okay, did you find this one back here?
No, but I can right now.
Okay, so I found the first one here as 90. I just need someone to find that one for me.
Oh, frick. I got it. Don't worry.
Okay, she's on it.
my way. The little cursor's so slow.
That's what I was thinking it should be.
Yeah.
-270? How far is it from -270 over to +90? From -270 to +90. I would do this. What is 90 minus -270? And don't type it in like I did with the cosine there. 90 minus -270.
Oh, what the heck? Oh.
Right? Because you're going backwards 270, and then you got to add on an extra 90. Maybe even just do this. What's 90 plus 270? 90 into the positives, 270 into the negatives. It's 360. Okay, let me stop here because I think I'm starting to lose you guys here. The reason why the period is 360, that's what a circle is for degrees.
Yeah.
Does that make sense? But I got to point out one thing here. It's 360 degrees if you're working in degrees, or if you're working in radians, it's 2 pi. Because 2 pi is how many radians fit inside a circle. So I think I'll leave that there. We'll do the cosine graph tomorrow. Let me do a quick summary here. Today's kind of a bit of a hodgepodge of random stuff that's really meant to be a preamble, because tomorrow's lesson is really like the big one where I want to focus on these graphs. Today I wanted to review for you how angles work a little bit, introduce to you the radian concept, which is really weird, hey? It's a new way of measuring angles. And then just show you what these graphs look like, just very basic. If you have your assignment nearby, maybe I can just show you some of the questions you're going to be asked to solve here. Like, here, I'll put it up on the screen even. Everybody get a copy of the assignment? Find like say number 7 here. can you see how these graphs right here, the wave kind of concept, these are now sinusoidal graphs. So the three things I'm going to be asking you to do more tomorrow is find me where the middle of the graph is, find me how tall the graph is, that's the amplitude, and then find me the period of the graph, which is like how long does it take to repeat itself. Okay. We can probably do this a little bit. Like for example, on graph 7a, I feel like the middle of the graph probably goes right about here. So it looks like I can put a line right across at about -1 probably. Does that make sense? On this graph right here, it looks like the middle of the graph might be at about 4 perhaps. Make sense? This graph right here, the middle of the graph might be at, what's the middle there, maybe 3? That makes sense? So tomorrow we're going to talk more about these equations and how to work with them based on learning, 1, reminding you angles, 2, working off of like, okay, now we have to be able to do radians. I guess another quick point here. You see how this graph right here lists degrees after each one of these? This one right here does not. So these graphs right here must be radian graphs. And this graph right here must be a degree graph. Does that make sense? And then lastly, I just want to introduce to you those 3 terms, midline, amplitude, period. Sound good? Okay, let's stop here because it's been an hour. Take a 5-minute break. When you come back, almost everyone here has something they should be working on. I'm not going to change my ways and like say that you can't go home early, but guys, if you're not done stuff, you shouldn't go home early because you're putting your marks in jeopardy. Okay, so catch up on whatever it is you need to catch up on. Journals. I'm not going to add any more stuff to the journals, by the way. We're just going to leave it where it is right here. So if you've been doing journal entries all the way along up till now, you're good. What did we calculate in that room the other day there? You needed to have like 45 of them. So like if you're behind on that, I mean, that's supposed to be the practice to get you kind of working on it. So anyways, take a break here. And when you come back, you got half an hour to do stuff.